Gentlemen, so right now what we're going to do is we're going to look at this example. It's a system. It's a system of linear equations, and we're going to try to solve it, and then we're going to try to interpret the solution uh, geometrically, so that we can see why it makes sense that the solution is the way it is. Okay. So the first thing we're going to do is we're going to decide whether we want to solve it by elimination or whether we want to solve it by substitution. Okay. So in my personal opinion, I feel it's better for us to solve it by elimination. So we're gonna do it that way. By the way, I apologize that this is kind of scrawled out at the bottom. But so the rules for elimination or Gauss elimination are as follows. To convert a system of linear equations to an equivalent linear system, remember that two systems of linear equations are equivalent if they have the same solution set, okay? We can, number one, we can interchange two of the equations. Number two, we can replace one of the equations by the sum of any two equations. Now, in this case, there's only two equations, so it kind of seems like trivial, or it kind of seems like it's overkill. But if you were dealing with like more equations, then of course this makes sense that you could it makes more sense that we would like replace an equation by the sum of any two equations. And number three, we can replace an equation by the multiple of that equation by a non-zero constant. So what that basically says is that for any equation in this linear system, we can multiply one of the equations by a constant that's non-zero, and we will recover an equivalent system. So now, in this case, what I can do, for example, is I can say, okay, I can divide this one by 3, and I can divide this one by 2 so that I can match up the x. Okay, or in fact, what I could do is I can multiply this one by 1/3 and this one by -1/2. So it would be this one positive 2 and this one -2. So I'll be able to then replace one of them by the sum so that the x term goes away, for example. So I'm going to codify that by saying 1/3 of my row 1, which is my first equation, will be my new row 1, and -1/2 of my row 2 will be my second equation. Okay. By the way, this notation I'm using here, I want you to use similar notation so that you can get used to so that you can be able to, when you look back on these notes, you can see exactly how I translated this system into the next system that we're going to have. Okay, number 1 and number 2, so that if you make a mistake in the calculations, you can systematically go from one system to the other using the rules to see where the mistake is. And also, this notation will help you prepare yourself when we're going to talk about matrices. And we want to talk about operations in matrices, you'll see that I'll use the same notation. Okay? So now 1/3 of R1 becomes our new R1. Okay? What's 1/3 of 6? That's 2. So it'll be 2x minus, what's 1/3 of 2? It'll be 2/3 y equals, what's 1/3 of 8? It'll be -8/3, right? What's -1/2 times 4? That's -2x. Well, -1/2 times 4 is -2, but of course I'm saying -1/2 times 4x, so it's -2x. What's -1/2 times -7y? That'll become plus 7/2 y. And then finally, what's -1/2 times 28? That's going to be -14. Okay. So we've gone from this system to this equivalent system. Okay. For example, and let me just show you how we would have gotten some of these numbers. So how did we get 1/3 times 6? We multiply 1/3 times 6. We can't do it directly, but we can rewrite the 6 as a fraction. So it would be 1/3, times 6/1. And now we have two fractions, and we know that we can get the product of these two fractions by getting the fraction whose numerator is the product of the numerators, so in this case 6 times 1, which is 6, and whose denominator is the product of the denominators, in this case 3 times 1, so that's 3, and of course 6 divided by 3 is 2, right? So that's how I got that 2. How did I get 1/3 times negative 2? Well, first of all, it's a positive times a negative, so it'll be negative. And 1/3 times 2, I can do it the same way. You see 1/3 times 2 is 1/3 times 2 over 1. And then, of course, how do I get the product of two fractions? I multiply the numerators to get the numerator of the product. So 1 times 2 is 2. I multiply the denominators to get the denominator of the product. 3 times 1 is 3. How do I get negative 1/2 times 4? Using the same process, right? And of course, in this case, it's a negative times a positive, so it'll be a negative. How do I get the negative 1/2 times the negative 7? Well, the negative times the negative makes it positive, and of course, the 1/2 times 7, you can do it just like this, right? So 1/2, times 7 is the same thing as 1/2 times 7 over 1, which of course, how do we get the product of two fractions? We multiply the numerators to get the product of, we multiply the numerators to get the numerator of the product. So 1 times 7 is 7. We multiply the denominators to get the denominator of the product. 2 times 1 is 2. And see, that's how we got the 7/2. And then of course you can do these ones the same way. Okay. So now we ask ourselves, what is the next step in solving this equation? So in this case, because of the way I chose the numbers I was going to multiply these equations by, I arrived at 2x being the x term on the first equation and negative 2x being the x term on the second equation. So I'm going to replace this second equation with the sum of these two equations. So what I'm going to say is that my R1 is going to go unchanged, but my R1 plus R2, in other words, my equation 1 plus my equation 2, will become my new equation 2, okay? Which I'm going to denote like this. R1 plus R2 is going to be R2. So what I can do is I can just copy over my first equation, 2x minus 2/3 y equals to negative 8/3. And then I need to figure out how to add these. Now, the 2x plus the negative 2x, that's the easy ones. That's just 0x, so I don't put anything there. What about negative 2/3 x, negative 2/3 y, plus the 7/2, okay? To figure out what my y will be, okay? So I'm going to calculate that explicitly here. Now you might see here, aha, David, these are two fractions. They don't have the same denominator, so what are we going to do? What we're going to do is we're going to have to multiply each of them by something, a fraction, that will allow us to put them on the same denominator. Well, to put the products on the same denominator, okay? Now, of course, that fraction, each of those fractions are going to have to equal 1, but they're going to have to be chosen in such a way that, for example, when I multiply these two, I'm going to get a number, and when I multiply these two, I'm going to get a number, and those numbers have to be the same. They're going to have to be a common denominator. So in this case, 3 and 2, we know, 6 is a perfect candidate, because I can multiply 3 by a number to get 6, namely 2, and I can multiply 2 by a number to get 6, namely 3. So in this case, I can put here 2 over 2 and 3 over 3 here. This gives us, now I can multiply these fractions just as before, so this becomes negative 4 over 6, and I can multiply these two fractions as before. 7 times 3 is 21 over 6. And now I ask myself, what is negative 4 over 6 plus 21 over 6? This will be 17 over 6. And you might say to me, David, why is that the case? Well, once they're on the same denominator, I keep the denominator, and I just add the numerators. In this case, negative 4 plus 21 will be 17, okay? Okay. So let me write that here. So here, this will be 17 over 6 y is equal to, and then I have to add these together, okay? So I have to add negative 8 over 3 plus negative 14, okay? So now I have to do this one. How am I going to do it? Are they even fractions? No. So what I have to do is I have to make the 14 into a fraction. I'm going to set it as 14 over 1. And now they don't have the same denominator, so I'm going to actually end up having to multiply the 14 over 1 by some other fraction, which of course must equal to 1, but which must have a denominator which will allow me to multiply with the 1 in such a way that I can get 3 as the common denominator for both of them. And of course, in this case, I can multiply 1 times 3 to give 3. So it'll be 3 over 3, okay? Now I'm going to add these two. First, before I add them, I'm going to simplify this right-hand side. So I'm going to get negative 8 over 3 plus negative 14 times 3. Let's do that together. 4 times 3 is 12. So I bring down my 2 and I carry my 1. 3 times 1 is 3, plus 1 is 4, so it's 42. So I get negative 42 over 1 times 3 is 3. Look what's happening here. I'm adding two numbers with the same sign. So what I do is I keep the sign and I add the absolute values to get the result. So I'm going to have a negative. I keep the denominator because I'm adding two fractions with the same denominator. And then the numerators, since they both have the same sign and I'm adding them, I just add up their absolute values to get the value of the sum. So what is 42 plus 8? That's 50. So this will simplify to negative 50 over 3. Like this. In this case, it was different. I was adding two numbers of opposite sign. So I keep the sign of the one with the bigger absolute value. If I look at the absolute value of the 21 over 6, it's 21 over 6. If I look at the absolute value of the negative 4 over 6, it's 4 over 6. The 21 over 6 having the larger numerator and with the same denominator has the larger absolute value than the 4 over 6. So the result of this sum will have to be positive, as the 17 over 6 was. And how did I get the 17? Well, because we're adding two numbers of opposite signs, I look at the absolute values. In this case, let's just look at the numerators, the 4 and the 21, and I subtract the smaller absolute value, which is 4, from the larger absolute value, which is 21. And of course, I ask, can I take away 4 from 1? I cannot, of course not, because 4 is bigger than 1. So I have to borrow from the 20. That becomes a 10. This becomes an 11. 11 minus 4 is 7. And then 1 minus 0 is just 1. And that's how I got the 17 over 6. Look, so now here, we're at a very nice situation. Okay. So if you look at this equation down here, I got 17 over 6. Y is equal to negative 50 over 3. So that means that I can get the y by itself. So what I'm going to do is I'm going to divide the left-hand side by 17 over 6. I'm going to divide the right-hand side by 17 over 6. And I see, aha, this goes away. I'm left with y equals, what happens when I divide by a fraction? I multiply by the reciprocal. So I'm going to have negative 50 over 3 times 6 over 17, because that's the reciprocal of 17 over 6. Now I'm going to perform this calculation, okay? So a negative times a positive is a negative, okay? That's great, it's a negative. I know that 50 times 6 is actually going to be 300, believe it or not. And I know that 3 times 17 is going to be 51, okay? So let me show both of those calculations to you here. What is 6 times 50? Okay. 6 times 0 is 0. 6 times 5 is 30. You can see that it's 300. What is 3 times 17? 3 times 7 is 21. So I bring down my 1 and I carry my 2. 3 times 1 is 3, plus 2 is 5, 51. And so you can see that that is my value of y. Okay. Now I want to find out what is my value of x. In order to find out my value of x, I have to plug it into one of these equations. Okay. So for example, let's say I take the first equation, which is the 6x minus 2y equals negative 8. So let's do that together here. First, I'm going to save that y value over here so that I can have lots of room to do that calculation. So I know that the y is equal to negative 300 over 51. Okay. So what I want to do is I want to use the value of y that we got to find out what the x is, right? So what I need to do is, first of all, I want to observe, and I can see, aha, this can all be divided by 2, and it'll simplify our equation. So let's do that first. So 3 times x minus y is equal to negative 4. Let me now add the y to the other side, because I want to get the x by itself, right? And so here I've gotten 3x is equal to y minus 4. Then I can divide by 3 both sides, divide by 3, and I get that x must be y minus 4 divided by 3. Okay? So now I can plug in. My y is negative 300 over 51. And I'm going to subtract 4 from that. And then I'm going to divide that by 3 to get the result. So let's do that calculation together. Negative 300 over 51 minus 4, let's say 4 over 1, because we know we're going to have to convert it into a fraction and do the subtraction. Now here, because we're fortunate that this fraction has the denominator 1, I know I can just multiply it by 51 to make it have the denominator 51. So that means that I can simply multiply it by 51 on the bottom and 51 on the top. Okay? So this will become negative 300 over 51 minus, and if you multiply 4 times 51, let's do that here. 4 times 1 is 4. 4 times 5 is 20. You can see that that's 204. So it'll be minus 204 divided by 51. Like this. You can see that this one will give us negative 504 divided by 51 on the numerator of the equation. Okay? So now we can write this as, the numerator is negative 504 over 51, and that's all divided by 3. Okay? So now we're going to actually perform that calculation. Okay? It's going to be a beautiful thing. We can't directly divide by the number 3 though. We must convert it into a fraction. So we're going to have, okay, this is going to be negative 504 divided by 51 divided by 3 over 1. And how do I divide by a fraction? I multiply by the reciprocal. So this is going to become negative 504 over 51 times 1 over 3. And so then this is going to become negative 504 divided by, and if you do 3 times 51, you get 3 times 1 is 3, 3 times 5 is 15, you get 153, so it's 153, okay? And then here, you might say to yourself, okay, David, can we simplify this fraction? And the answer is actually we can. We can actually simplify both of these fractions. So let me show you something very nice. It turns out that if you add up the digits of a number and they add up to a number that's divisible by 3, then you can divide it by 3. Okay, so of course that's a specific test for dividing by 3. So here, if I add the digits of the numerator is 504. If I add the digits, 5 plus 0 is 5 plus 4 is 9. And if I add the digits from the bottom, 1 plus 5 is 6 plus 3 is 9. I can see that both the numerator and the denominator here can be divided by 3. And if I do that, let's divide, so the bottom, I know it's actually 51 times 3. So I'm going to divide the bottom by 3 and I get 51. And I know that because we just got it like that, right? The numerator though is going to be different. We don't know what the numerator is divided by 3, so we're going to do the division. 3 goes into 504. 3 goes into 5 once. 1 times 3 is 3. 5 minus 3 is 2. I bring down my 0. 3 goes into 20 6 times. 6 times 3 is 18. 0 minus 8, I can't do that, so I borrow. This becomes a 1. This becomes a 10. 10 minus 8 is 2. 1 minus 1 is 0. And then I bring down my 4 like this. And I ask myself, how many times does 3 go into 24? it goes in 8 times. So I can see that this is negative 168 over 51. And you can actually see, by the way, it may not be that easy to see this, but if you add 1 plus 6, you get 7. If you add 7 plus 8, you get 15. So you can again divide it by 3. So this will again simplify. And also the 51 in the bottom, 5 plus 1 is 6. 6 is divisible by 3, so this will also simplify. Okay, so let's divide both the top and bottom by 3 to get this simplification. 3 goes into 168. How many times? Does 3 go into 1? No. Does 3 go into 16? Yes. We know that 5 times 3 is 15, so it goes in 5 times. So 5 times 3 is 15, like this. 6 minus 5, that's 1. 1 minus 1 is 0. I bring down my 8. I ask myself, how many times does 3 go into 18? 6 times. 6 times 3 is 18. We subtract, we get 0. So we know that the top will be 56. So negative 56 over, and then we ask, how many times does 3 go into 51? 3 goes into 51. Well, 3 goes into 5 once. 1 times 3 is 3. 5 minus 3 is 2. I bring down my 1. I ask myself, how many times does 3 go into 21? 7. 7 times 3 is 21. And I can subtract these, and I see I get 0 again. So the denominator here is 17. Now that one does not simplify any further. So my x in fully simplified form is going to be negative 56 over 17. Okay. So what about the y value? Okay. So if you notice the y value, the numerator is 300. That one's obviously divisible by 3 because 3 times 100 is 300. And of course, we already saw that 51 is divisible by 3 because we saw it gives us 17 when you divide it by 3. So this can be simplified to negative 100 over 17. So basically, our solution is, we can write it like this, or we can express it as a point, right? So negative 56 over 17, comma, negative 100 over 17. So in other words, the key point I want you to observe here is that we have a unique solution, okay? And the question I want to ask you is, why is that the case? Why do we have a unique solution? So to kind of figure out what's happening here to kind of figure out what's happening here, why is it that we got a unique solution? What I'm going to do is I'm going to show you some of the associated geometry of this problem. So what I want you to observe here is the following. Look at this system of linear equations, okay? The system of linear equations is 6x minus 2y equals negative 8. And it's 4x minus 7y equals to 28. So in this case, we're very fortunate because this is in 2 dimensions, so it's very easy for us to rewrite these equations as lines. You see, these are they are actually lines. Let's take the first one. I can rewrite 6x minus 2y equals negative 8 as, first of all, I can add the 2y to the other side. And I can add 8 to the other side as well, like this. And so I can end up with, this goes away, and I have 2y is equal to 6x plus 8, because these go away too, right? Negative 2y plus 2y, those are gone. Boop. And then you look at this equation, I can divide both sides by 2. And I can see, aha, this is going to be y equals 6 divided by 2 is 3x plus 8 divided by 2 is 4. Okay? Okay. So you can see I can replace this first equation with the equation y equals 3x plus 4. Okay? What about this second equation? The 4x minus 7y equals 28. So what I could do is I can add the 7y to the other side. I can subtract the 28 to the other side like this. And I get 4x minus 28 is equal to 7y. Then I can divide both sides by 7, right? To get the y by itself. And I can see that the y, which will be the right-hand side of the equation, will equal to 4 over 7x minus, what's 28 divided by 7? 4. So it'll be minus 4, like this. So the second equation can be rewritten as y equals 4 over 7x minus 4. Okay? Now you observed here that because I used the rules of algebra to transform this equation into this equation, they represent the same line, okay? Same thing with that situation over here. I transformed this one into this one without changing how should I put it? Because I used the rules of algebra and the rules of arithmetic to transform this equation into this equation, they still represent the same line. And if you want proof of that, you can plug in two values of x in the original equation to get the 2 points, to get the associated y values. And if you do that with this, you'll get the same 2 points. And once you do that, you know that in geometry, through any 2 points, there is exactly one line. Okay? But basically, what I've done is I've taken this system and I've rewritten it like this. And what does that tell us? Well, what that tells us is that geometrically, these are two lines that have a different slope and different y-intercepts. Okay? So if I were to do a rough graph of this like this, let's say, okay, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, right? And then 1, 2, 3, 4. The bottom line, let's say the y equals 4 over 7x minus 4. It'll cross the y-axis over here at negative 4, right? So I'm just going to put a little circle around that. So we know that that's the intersection point. And the slope is 4 over 7. So that means I'm going to go up 4 and then 7 to the right. So I'm going to go 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7 to find another point on the line. So then I would connect these like this. Okay, so this is going like this. Off into forever. Okay, obviously, this is the straightest line you've ever seen in your entire life, and there could not possibly be another line that's more straight than this one that has ever been drawn or that has ever been conceived. Anyway, I'm just kidding. It's ugly, but the point. But you're gonna get the point soon. Now, what about the first equation? So I'm drawing this one in blue, of course, as you might have already imagined, right? So this one's in blue, and of course the other one's gonna be in black, right? 3x plus 4. The y-intercept is 4, right? You see? So I can make my first point. I start from 0. 1, 2, 3, 4. It's that point. And it has slope 3. That means I'm going to go 3 up and 1 to the right. So 1, 2, 3, and 1 to the right. Like this. And so then I'm going to draw that line, and it's going to drop down like this. You see? And you can see that because the slopes are different, they're going to intersect somewhere. And in fact, where are they going to intersect? Right? That's the question now. Where are they going to intersect? They're going to intersect at this point. If you notice, 17 times 3 was 51. So this is somewhere between 3 and 4. So let's say, let me see here. So let's say 1, 2, 3, 4, right? So somewhere in between 3 and 4 is that point. And what is this point? It's negative 56 over 17, comma, negative 100 over 17. Now, if you think about that one, okay, what is that? Well, 17 is almost 20, right? So 100 over 17 is going to be, let me see here. It's going to be, a little more than 5, but it's not going to be like 6. So it's going to, but in any case, the actual value is going to be negative 100 over 17 as we calculate, okay? But if you were looking at it on your graph paper, it would be like somewhere like over here, like in the 5 to 6 region. Let me use my calculator here real quickly. Yeah, like 5.88, more or less. We could have done long division. But the most important part of this is I want you to see the following. We started off with a system of linear equations in two variables. We found that it had a unique solution. And so then we want to figure out why is that the case. So in this case, it's very nice because we have a 2x2 system. We can express it in terms of just y and x. And so we're already familiar with graphing lines. And we can see that each of these equations are lines. So why not express them in slope-intercept form? And we see that they have different slopes and they have different intercepts. But in any case, the moment they have different slopes, we don't care about the intercepts anymore, right? They have different slopes, so therefore they must intersect only once. And we see that that intersection point is the unique solution. Okay? And now, and just to recap, or just to preview the other ideas, if they had had the same slope and a different intercept, a different y-intercept, they would have been parallel. And if they had the same slope and the same intercept, then they would have actually been the same line. In the case of the same slope and the different intercept, where they're parallel, that would be no solution. And in the case of the same slope and the same intercept, then that's infinitely many solutions, because they would actually correspond to the same line. Okay? I hope you've enjoyed this example, and I look forward to seeing you again soon. Thank you so much.